Using Euclid's division algorithm, find the HCF of the following. So we first take up the first sum here. So here we have HCF of 135 and 225. Now we divide these numbers. So here I write 135 and 225 I divide by 135. So you get 1 and this will be 135. You subtract, here is 90. So let me write the division algorithm, that 225 equal to 135 into 1 plus 90. And the next step, I divide again 90, but now my dividend becomes 135. So when I do this division, there is 1, this is 90, and when I subtract, here I get 45. So let me write this out. So this was 135 was equal to 90 into 1 plus 45. Now for the next division. Here my 90 will come out here. So I divide now 90 by 45 and it is 290. So my division is now complete. My remainder is 0. So for this one I have 90 equal to 2 into 45 plus 0. Now the HCF of 225 and 135 will be equal to this last divisor, which in this case is 45. This is my last divisor here. This is always a HCF. In this case, here is the HCF. In the second one, we'll take 196 and 38220. So first we'll do the division. So we have 38220 divide by 196. On dividing, here you do 1, this is 196, you subtract, you get 186, you bring down 2, you now put 9 here, so you get 186, 2, you subtract, not 18, it's 17, this is wrong, 1764, the normal division, subtract, remainder here will be, for the next division you have 5, so 980, remainder is 0. So when we're doing our division algorithm, and we write 38220 equal to 196 into 195 plus 0. Now in this case the HCF will be the last divisor. Here this was our last divisor. We did just one division here. So 196. So HCF equal to 196. Here we need to find the HCF of 867 and 255. So we carry on the division. We take 867 and divide it by 255. So here we'll have 3, so it will be 765. We'll subtract 201. Let's write the division algorithm. So for the division algorithm, we have 867 equal to 2, here 255 into 3 plus the remainder here 102. And the next step, 255 becomes the dividend. So here we divide it by, here's 255. Now on dividing this, here we get 2. So this becomes 204, subtract, that is 51. So let's write the division algorithm. So we have 255 equal to divisor into quotient, 102 into 2 plus remainder plus 51. Now for the next step, here we'll take 102, this becomes the dividend. So 102 we divide, and we know we'll put 2 here, 102 we subtract, remainder 0. So now for the next division algorithm, we have divided 102, and 102 is 51 into 2 plus 0. The last divisor is 51. This was our last division, right? And 51 is the last divisor here. So that's the HCF. So HCF is always the last divisor. So HCF of 867 and 255 equal to 51. See here, we did one division at this point, then we did a second division here, and this was our last division. The divisor of the last division, in this case is 51, becomes the HCF. An army contingent of 616 members is to march behind an army band of 72 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So here we have an army contingent of 616 members. So this is a group of 616 members, and they are marching in columns. So let the number of columns say 1. We do not know how many columns. So let the number of columns be x. Now if the number of columns be x, we definitely know x is factor of 616. Now in the second part of the sum, they say there is a army band of 32 members marching just behind them. So let's draw, this is the army band, and in the army band they have 32 members, and these 32 members also are marching in columns, and the number of columns are the same. They're all in these columns. Let's go over it again. So we have 616 here, and we have 32 members here, and they're marching in columns. So we have like maybe one column here, 2 columns here, the third column, and so on. We do not know how many columns, so we say let it be x columns. The band is also marching in the same number of columns, so they're just one behind the other this way. So let these columns also, we do not know. Let the number of columns for the band also be 30, be also x. So x is should be the factor of 616, and x is also factor of 32. Here x is factor of 616. Because we know 616 is divided into x columns, and the band behind them 32 is also divided, all the members of the band are also divided into x columns. So x is factor of 616, and x is also factor of 32. So for this sum, we need to find the HCF. Both are factors, HCF of 616 and 32. So we'll go ahead and find HCF of 616 and 32. So 616, here we divide by 32, and this is 1, you get 32, you will subtract, remainder here is 2, two 9, then you bring down 6. Now again, when you divide now, here you get 9, and 9 will be 2, 8, 8. This is still the same division. Here we subtract, we will get 8. And now for the next remainder is 8. So let's try the division algorithm. 616 here is equal to 32 into 19 plus 8. That is 32 into 19 plus 8. Now for this next division. In the next division, this 32 becomes our dividend. So we write 32 here. We divide. This is 4. 32, 0. This is our last division. So 32 equal to 8 into 4 plus 0. Here is the last divisor. And this last divisor becomes the HCF. So here is this. So the HCF equal to 8. So the number of columns are 8. So to go back to the sum, we had 616, and the 616 would be divided into like 8 columns. 2, 3, 4, 5, 6, 7, 8 columns. And when it comes to the band, this band of 32 would also be divided into 8 columns. They're one behind the other. See, this also into 8 columns. So here 8 columns here. 8 is a factor of 616, and 8 columns here. 8 is a factor of 616 of 32. So here this factor 8 had to be a common factor of both. It had to be of 616 as well as 32. So basically in the sum we took 616 and we took 32 and we found the common factor, the highest common factor, hence we found HCF. Before we get on to the other sums, let us first have a little explanation like what are even numbers. Even numbers are numbers that have factor, one of their factor is 2. An example of even numbers would be like say 6. Why? Because it is 2 into 3. Then you have 18. 2 into 9. Or you have 54, which is 2 into 27. And in all such numbers, even numbers, you will see it has a factor 2. So in general, an even number could be written as 2m. 2 into some number. Let's take some more examples. Like 10. 10 is an even number because it is 2 into 5. That is 2m. Let's take 120. 120 is an even number because it is 2 into 60. Means it can be written as 2m. 2 into another number. Or we take the number say 42. It can be written as 2 into 21, which is 2m. So all you need to remember now, every even number is written in a form of 2m. Now what would be odd numbers that do not have 2 as factor? Example 7. You cannot write 7 2 into something, but 7 can be written as 2 into 3 plus 1. Let's take another even an odd number now. See, we take up 13, odd number. 2 into 6 plus 1. Or we take up another odd number, say 41. And that would be 2 into 20 plus a 1. We take up a number, say 55, and this is 2 into 27 plus 1. So in general, if you notice in each of this, you write it as 2, then you have m plus 1. In this case also you have 2 into 6, which will say m plus 1. In the next case too, you have 2, this is the m plus 1. And here again you have 2m, so 2m plus 1. So every odd number, here odd number, will be written as 2m plus 1. Let's recollect what even number was written as. In the earlier slide we have done even number is always written as 2m. So if any number is written in the form of 2m, it has to be even. And if a number is written as 2m plus 1, it has to be odd. We'll now learn a little more in detail about Euclid's division lemma. Now Euclid's division lemma says any number a can be written as bq plus r, where r is always greater or equal to 0 and less than b. Let's go ahead and see what is the meaning of all this. So we take first b, say equal to 5. And we'll take up a set of numbers and use the division lemma there. So we'll take up these numbers. I'll just write down the numbers first. I'll take up 5, then we have 10, 5 we take up in order, 5, 6, 7, 8, 9, 10, 11 and so on. So we take 5 is equal to, now 5 can be written as 5 into 1 plus 0. We take 6, we have taken b as 5, remember. 6 can be written as 5 into 1 plus 1 will be 6. Then 7 can be written as 5 into 1 plus 2. Remember the first one we always take 5 because we take b as 5. 8 can be written as 5 into 1 plus 3. 9 would be written as 5 into 1 plus 4. Then 10, 5 into 2 plus 0. And then we have 11, 5 into 2 plus 1. Take a look at the r. So we have written a, bq plus r. But look at the r. These are the r's. In this case it is 0, then it is 1, then it is 2, then it is 3, then it is 4, then 0 again, and 1, and so on. If you notice, the r is never greater than 5. R is always less than 5 because we took B equal to 5. If B was equal to 5, the remainder will always be less than 5. We'll take up another example. So we know our division, Euclid's division lemma, A equal to BQ plus R. Now in this case, we will take our R as, B we will take as 3. And we'll take up a set of numbers. We will start, say, from 5, 6, same numbers, 8, 9, 10, 11, 12, 13. And we'll start writing them off. Remember, we've taken B as 3. So everywhere we're going to do 3 into 5 will be 3 into 2 plus 1. Now plus 3 into, this is wrong, 5 will be 3 into 1 plus 2. 6 will be 3 into 2 plus 0. Keep a check on what your R is. Then we got 7. 7 is 3 into 2, that is 6, then plus 1. 8. 3 into 2, 6, that is plus 2. Then 9. 3 into 3 plus 0. Then we have 10. 3 into 3, 9 plus 1. Then we have 11. 3 into 3, that is 9, that is plus 2. And then in the end we have 13. 3 into 3, 9. 3 into, we've taken 13, we should have taken 12 here. So we'll just take up 12. Is 3 into 4 plus 0. So have you noticed the pattern of R? All these are R. And let's look very carefully. It goes to 0, 1, 2, then again 0, 1, 2. It never crosses 3. So in this case, your R is always greater than or equal to 0, but it's always less than 3. Because if B is 3, your R will be 0, 1, 2. It will never cross 3. We take yet another example, A equal to BQ plus R. In this case, we'll take, say, B is 4. We'll write a set of numbers, say, starting from 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And let's get on. So remember, we have taken B as 4, so it is 4 into 1 plus 0. 5 will be 4 into 1 plus 1. 6 will be 4 into 1, that is 4 plus 2. Remember, we've got to take this first number always 4, because we have taken B as 4. This is not 2 plus 1 plus 3. Now since we have taken B as 4, right now we can make out by the earlier patterns that the R will be 0, 1, 2, 3. That's it. It will not going to be 4. So here see 0, 1, 2, 3. Now we have 4 into 2, this is plus 0. 4 into 2 plus 1. 4 into 2 plus 2. 4 into 2 plus 3. That's it. It will be only till 3. It won't go beyond. So we see that the R doesn't go beyond 3. So here, suppose we were to take another number. Say take B equal to 6. Then the R would be 0, 1, 2, 3, 4, 5. It can't be 6. So the A could be either 6Q or A could be 6Q plus 1, or A could be 6Q plus 2, or 6Q plus 3, 6Q plus 4, 6Q plus 5. Next, if you take, say, b equal to 5. So what could your a's be? Any number could be written as 5q. Now this, b is 5, your r will be 0 or 1 or 2 or 3 or 4. So it will be aq plus 0, we don't write the 0. So aq plus 1, or it could be aq plus 2, aq plus 3, aq plus 4. This would be the different possibilities. We take yet another example, say b equal to, say, 3. Then it could be a could be 3q, so it could be like 0, 1 or 2, that will be your r. So a will be 3q plus 1, 3q plus 2, and that's it. Show that any positive odd integer is in the form of 6q, 6q plus 3, 6q plus 5. So again, by Euclid's division lemma, we have a equal to bq plus r. Now if you notice here, we have to find 6q plus 1, 6q plus 3 and 6q plus 5, which means in this case we'll write a equal to 6q plus r. Now if b equal to 6, so what is r equal to? That we've done in the earlier, we said r could be 0, 1, 2, 3, 4, 5. So let's take case 1. Case 1, where r is 0. So we have a equal to 6q. Then we'll take up case 2, where r is 1. So we have a equal to 6q plus 1. This is case 2. Then we take up case 3. So case 3, that is a equal to 6q plus 2. Now for the first one, we have a equal to 6q. A equal to 6 is 2 into 3q, right? 2 3s are 6. Now we've already have seen that what are even numbers. Let's just revise that. What were even numbers? Even, that could be written as 2m, and odd was, those could be written as 2m plus 1. So here we have a equal to, this will take as m, so this written as 2m. Now a equal to 2m, and this would definitely be even. We want to pick up only the odd numbers. Let's go to the next one. So that was even. Now a equal to 6q. So a equal to, for 6q we'll write 2, 3q plus 1. So a equal to, for aq I'm putting m. So that becomes 2m plus 1. And 2m plus 1 we know is odd. Here 2m plus 1 is odd. So this will be odd. So here odd. We need to pick up only the odd. Now go to the next one. That is 6q plus 2. So a equal to 2, 3q. See, the 6q I'm making 2 into 3 plus 2. So a equal to, I'm taking 2 common out. So 2, what will happen here is 6q plus 1. Now a will be written as 2, and this can be written, it's in the form of 2m. 2 into something. So we know this must be 2m is even. We don't pick this up because we want only odd numbers. Next we have to do, we have taken up 2, so we'll take up 3. Then we will take up a equal to plus 4. So So let's take up the 3. So we have A equal to 6. I'm going to write it as 2, 3q plus 3. So A here be 2, 3q, so 2q, and this 3 I'm going to break it up as 2 plus 1. Now I take common out from here, so we get A equal to, here 2 common out, so what remains here is 3q plus 1, and this is plus 1, so A is 2m, this is our m, plus 1, and this is now odd. 2m plus 1 is odd. Next we take A equal to 6q plus 4, so A equal to 6q plus 4, and straight on from here I can take 2 common out, so it will be 3q plus 2, so A equal to 3m, and this is even, 2m, this is even number. We need to pick up the odd one, so we pick this one also, this was odd, so we pick this up. And for the last, A equal to 6q plus 5, so A equal to, for 6 I'm putting 2 into 3q, and for 5 I will put here 4 plus 1, so A equal to, here I take common out, I'll take 2 common out, so what remains here is 3q plus 2, here plus 1, so A equal to, this is m, 2m plus 1, and this works out as odd. So again this is odd. So when we go through, we saw the odd ones were 6q plus 1, 6q plus 3, and 6q plus 5. These were all odd. And why were they odd? Because each one of them, we wrote them as 3m plus 1. Use Euclid's division lemma to show that the square of any positive number is either 3m or 3m plus 1. So we start with Euclid's division lemma. And Euclid's division lemma is A equal to BQ plus R. Now here we have to write in the form of 3m, which means I'm going to take A equal to 3q plus R. And you know why I had taken B equal to 3. If B equal to 3, my R is 0, 1, 2. So I have 3 cases. I have case 1 where A equal to 3q plus 0. Case 2, A equal to 3q plus 1. Case 3, A equal to 3q plus 2. And here they want to know square of the numbers. In the next step, I need to find square of each. So first case, we say A equal to 3q. And the question was about square, so we squared it. Squaring, we have A square equal to 9q square, and A square equal to here. So the square of the number is 3 into 3q square. I've just broken up 9 into 3 into 3. So the square, A square, will be, I put m here, this will be 3m. Now I take case 2. In the case 2, if you recollect, everything is A equal to 3q plus 1, and we have to find square of the number. So we square, so we have A square equal to 3q plus 1 the whole square. A plus B the whole square, that is A square 2ab plus B square. Now with these two I take 3 common out. So I have 3, so what remains here is 3q square, 2q plus 1. You don't have to take q common out, just 3. and you'll understand why. Now here I have 3. For this I'm going to put as m plus 1. So I showed, remember I have to show the numbers are either 3m or they are 3m plus 1. So I've shown it is 3m plus 1. And for case 3, a equal to 3 plus 2. Again we square. So a square 3q plus 2 the whole square. A plus b the whole square. A square. 2ab will be 12q and this is 4. Now remember, we either have to show them as 3m or we have to show 3m plus 1. This was given in the question. So I take 9q square, here 12q, and for 4 I put 3 plus 1. 3 common out, 3q square, 4q plus 1 plus 1. Now here is my m. So this is 3m plus 1. So again I showed that this a square is 3m plus 1. Use Euclid's division lemma to show that the cube of a number is 9m plus 1 or 9m plus 8. So by Euclid's division lemma, we have a equal to bq plus r. And in this case, we are now going to take b as 3 because I have 9 here. And you probably ask me the question, why not take 9? Why take 3? But just by taking 3 also we get the answer. So we see here a equal to 9, not 9, we have to take 3 plus r. If we take 9, the sum gets longer. But let's see what happens when we take 3. When we take 3, r becomes 0, 1, 2. So our case 1 would be a equal to 3q. Then we find cube. Second case would be a equal to 3q plus 1. This is the second case. And third, a equal to here 3q plus 2. So we got to work just 2 cases. But what if we had taken 9? Suppose we take a equal to 9q plus r. Then we would have had much more cases. A equal to 9q, a equal to 9q plus 1, a equal to 9q plus 2, a equal to 9q plus 3, and so on till a equal to 9q plus 8. And this becomes very long. So you need not do this. You can do it just by using 3. And we'll see how we get it just by using 3. So we take case 1. Here we take this case. So a equal to 3q. And remember we have to do cube. This is cube. So we need to find cube of it. So a cube equal to 3q the whole cube. So a cube is 27q. And a cube, 27 can be written as 3 into 9 or 9 into 3. 9 into 3 cube. Right? So we did a cube equal to 9 into 3 cube. This 3 cube can be taken as m. So this is 9m. So we did the first one. That is 9m. Now we go to the next. A equal to 3q plus 1. Now remember we need to find the cube. So a cube plus 1 the whole cube. Now we use the formula here a plus b the whole cube. That is a cube 3a square b plus 3ab square plus b cube. This is now 27q cube. This will be 39q square. So this 2 would now be 27q square plus 9q plus 1. So a cube equal to, I can take 9 common out from here. So if I take 9 common out, this will come 3 cube not cube, we just take 9 only, because we need to show just 9m plus 1. So you just take 9 common out. So 3q square plus q plus 1. So now this becomes 9. This is m plus 1. So a cube is 9m plus 1. And now for case 3, where a equal to 3q plus 2. So cubing it, you get a cube equal to 3q plus 2 the whole cube. So a plus b the whole cube, you have a cube plus 3 a square b plus 3 a b square plus b cube. This is 27q cube. If you work this out, you will get it as 54q square. If you work this out, you will get it as 36q plus 8. Now from here, we are going to take 9 common out. So what remains in is 3q cube plus 6q square plus 4q plus 8, which means here I have 9. I will take, this is 9. This I'm going to write as m and plus 8. So in the first case I showed it was 9m. In the second case I showed 9m plus 1. In the third case I showed 9m plus 8. Here the sum is trying to tell us that any cube that you take can be written as 9m, 9m plus 1 or 9m plus 8. Like let's take a cube 27. 27 is 3 cube, right? And this can be written as 3 into 9. Let's take another cube, say 64. 64 is 4 into 4 into 4. So here's a cube, and now C64 can be written as 9, not 3, that is 9 into 7 plus 1, which means 9m plus 1. We take up yet another cube, like 5 cube. 5 cube is 125, and that can be written as 9 into 13 plus 8. So this can be written as 9m, that is, this is m plus 8, this 8. So you can take many other examples. Let's take another example, say 10 cube. 10 cube is 1000. It can be written as 9 into 1 plus 1 equal to 1000. That is 9m plus 1. So take up any cube. You will either be able to write it as 9 into a number, you will be able to write it as 9 into a number plus 1, or you will be able to write it as 9m plus 8, any cube.